So this is lecture 29 E51. So we talked about following things, which includes, like, starting from the first chapter, it's single stage amplifier, single stage single ended amplifier, right? In that also we also studied cascade as well. So if you remember, so Aishwarya, if I'm looking from top, what is the impedance if this is M1 and if this is M2? One more thing. What are you saying? Okay. Okay. So you're saying if this is M2 and if this is M1, then this is the okay, right? So you remember. Other than that, hmm? RO, okay. Was it RO1 or yeah, yeah. So you made a mistake. If you are looking from top, it's GM1 RO1. Sorry, GM2 RO2 times RO1. Right? If you are looking from here, V1. If I am looking from here, I am going to see only and only RO1. If I am stacking one more transistor on top of this one, if this is M2, then it's GM2 RO2. If I adding one more, then GM3 RO3 and so on. The last one will have only contribution of RO1, right? So this is what we learn. Thereafter we also learn about differential, where in differential we learn that small signal AC signal and common mode DC signal. Sometimes common mode equal to DC, sometimes it's not. If it is like both the inputs are tied together and same, then it's known as common mode. And differential is the one where it's 180-degree phase shift. Because of that, we found that there is some virtual ground. Here there is no virtual ground in common mode, and you can find out by keeping respective transistors in parallel, right? Because when we are um, giving two inputs same, and like there are some of the nodes where the voltage is same, so you can short them. And other than that, like we studied CMRR, which is uh, which is ratio of these two, and we also studied frequency response. In frequency response, we studied that as many number of effective number of capacitors you are going to see, that many number of poles will be there, and zeros are depending on how many number of capacitors are there, which are actually actually creating input to output transmission, and that is the zero, right? Maybe I can ask you like the design what Saurabh is designing. So this is V in, this V out. So how many poles will be there and how many zeros will be there in this circuit? This is correct, right, Saurabh? How many poles will be there and how many zeros will be there? How many effective capacitors are you seeing? You have to use Miller, of course. One of the effective capacitor will be here. Right? Then one is here, but one is here, one is here, one is here. If you solve this, you will get so many capacitors and so many poles you will see. Similarly, between V in and V out, you will see that there is a transmission. So from here to here, there is a capacitor, right? So there is a transmission from here to here. There is one more, which is here to here, so here, and of course through this path also there is a link. So either of them, which is higher one. So you will see, actually depends how you are doing the analysis, but 3 to 4 zeros you will experience, right? Our analysis says that it's like he solved with the KCL and KVL and he got same number of poles and zeros, right? So that's how like you can estimate the location of poles and zeros. That is what we learn, right? Just you have to use Miller, and you have to find out the capacitor, and using capacitor you can find out the effective resistance seen in the parallel of capacitor, right? That will give you the RC time constant, and then 1 by RC time constant. That's the pole in radian per second, and zeros is depending on how much transmission you are giving from V into V out. Other than that, the first topic of Opamp also we started working on, and that's two-stage Opamp, because we know that any circuit in feedback, if it is negative feedback, it's A by 1 plus A beta, where beta is feedback factor. If you are connecting in feedback like this, it's A by 1 plus A beta, and as A tends to infinity, this entire transfer function h of s is actually 1 by beta. So depending on only on ratio or whatever you are keeping as feedback, that is going to work. So this is already known theory to us, and that is what we are doing in Opamp. That even though this is infinite, this gain you are approximating to like minus Rf by R1 if this is the circuit, right? And there is no involvement of this gain as long as this gain is infinite. But if it is not infinite, then the answer has to be like this. Answer should include A also, the value of A in volts per volts. That has to be there. So for sufficiently large gain, we are going to add the stage. So one more stage, adding one more stage is going to give you not only the high gain, but it's also going to give you swing. So there are two stages. One can use 3 stages also. So in the first stage, we have used a differential amplifier whose gain, like achievable gain, is around how much? 30 dB, right? So 30 dB is achievable, and one more stage we are adding depending on our application. So that is going to give you the gain as well as the swing, because if you look at this, the output stage, which looks like this one, let's call it V out 1, and this is V out in total, and this is V out 1, this is V in, and this is V out. So this is second stage, which is like this, right? So this stage, can you tell me what is the ICMR for ICMR mean for this case? Mahima, ICMR mean. So you have to look at the input. Input is here. So downside. How much voltage you are seeing here? If I am holding a multimeter in my hand, how much voltage I am going to see here? This one is input. V out 1 is acting as an input of this one. Okay, if you don't like this, then let's call this one as V in 1, which is input of second stage. Second stage I have drawn. First stage is differential. So now tell me, how much voltage you are seeing here? ICMR mean VGS 2, whereas ICMR max, what do you think about ICMR max? So you have to start from here. Yeah, Surabhi, what do you think? VDD minus VDS1 plus VTH2, right? So this is how like we can find out the input common mode range. However, if you are looking at the output, OCMR actually, OCMR max and OCMR mean is actually deciding the swing, how much swing you can have. So what about the OCMR mean? Yeah, Shivam, VDS2. What about max? VDS1, right? So it's very simple. OCMR and ICMR. OCMR is actually deciding the swing, so you are going to have the higher swing. Very easily you can make these transistors in saturation because there are only two. You can easily achieve more than 250 millivolts, right? So this is what we studied, and we also studied that on the basis of parasitics, you are going to have the poles and zeros, right? So if this is the first stage of your two-stage amplifier, where this is diode connected, it's not identical like the previous case we were using VB. So if these are the capacitors as shown here, so in total how many capacitors are there? By the way, when we are doing this analysis, when there are capacitors, so is it small signal AC analysis or common mode analysis? Which one it is? Why it is so? Hmm. Won't be there. Yeah. So in that case, what will be the value of this node? Hmm? It has to be 0, right? It's a virtual ground. When you are taking small signal AC, it is going to have two signals which are differential to each other, right? In that case, this is virtual ground, right? So in that case, we are seeing or measuring the capacitors. So this is not so much useful, even though it's there. This one is useful, this one is useful, but this one can be kept here using Miller. So effectively there is one capacitor here, right? And one capacitor is somewhere here, right? So you can write down sorry. So you can write down the effective resistance looking into parallel of this capacitor, and you can find out the respective poles and zeros. Of course, there is one more capacitor at the input side, but that capacitor is actually in shunt with 50 ohm resistance, so this is going to be very far, so we don't consider that one. Otherwise there are 3 poles. Similarly, this capacitor is also very small one and it's going to be very far, so effectively there will be only one capacitor, but with the theory there are 3 poles and 1 0, right? So let's look at the same thing which we are doing last time. So it's a fully differential structure where this is not a diode connected, this is bias voltage. You can take the half circuit and remove rest of the part as a differential. So whatever is available at one side, same will be the total gain, right? As per our theory, half circuit you can take and you can remove this part, right? One of the part you can remove for AC analysis. So can you tell me what is the gain, by the way? What is the gain? AC gain is equal to AC gain equal to minus GM2 RO2 parallel RO4 GM6 GM6, that's correct, not 8. Input is here. By the way, this is actually DC. This is bias voltage, right? It's CMOS based input, right? This is the correct answer, right? What about the common mode gain? So in common mode gain, you have to consider entire circuit. Let's start with the first stage. So when this is tied together, if you are giving V in, right, then what is the common mode gain? Let's start with the first stage. What is the first stage gain? Because that will be multiplied by the second one. What is the first stage gain? By the way, this is, let's call this one is also M1 and this one is M3. And the resistance offered by this one is some RSS or R01, whatever you like, you can call it. So tell me. Yeah, Amit, right? Yeah, Amit. So what is the common mode gain? Sorry? Are you confident? You remember how to do it or no? So tell me the correct answer. R03 by 2 parallel with GM1 RO1 RSS. Okay. GM6 by 2. Let's call this one as 6. This one is 8. Yeah. Keep going. Yeah, RO8 by 2 with RO6 by 2. However, here there is one mistake. It has to be like GM2 GM6, right? This is correct, or RO3 in shunt with this one, but it's missing 2 GM1, right? Yeah.
First is I think it is RO1 by 2 in parallel with RO3 by 2.
Okay, I'm writing what you are saying. RO1 by 2
In parallel with RO3 by 2.
RO3 by 2
divided by
RSS
plus 1 by 2 GM1.
RSS plus 1 by 2 GM1. Yeah. So which one is correct? Yeah, upper wala, there has to be like some more term. Yeah, so this one goes to GM1 RO1 RSS and divide by this one. Now this is fine, right? Because it's a source degeneration, so it has to be added. And this one is correct, right? Okay, so if these are the correct things, just for okay. So now it's similar question which we were trying to solve 50 dB of small signal gain with 1 volt per microsecond of slew rate. So when it's 1 volt per microsecond, what we can find out? We can find out the current requirement or the tail current going from here, right? For that we need to know what is the capacitor here at the output. So that capacitor is the gate capacitance of this transistor. Similarly, the current flowing through this one is depending on the load capacitor, which I can take 1 picofarad, right? So can you tell me if it is 1 picofarad of load, how much current is required? By the way, current will tell me the bandwidth also. So I need to find out these things. By the way, supply voltage is 1 volt. VDD is 1 volt. Hmm? What 1 micro? 1 micro current you are saying? 1 micro ampere of current. Okay, you got 1 micro ampere of current. Okay. What about the bandwidth? So it has to be resolved, like the output has to be coming. If this is 1 microsecond, this is 1 volt, then you can make some budget of, maybe around 3 microsecond. This one is, so this will become 6 microsecond. So 1 by 6 microsecond, that's the bandwidth we require. Right? This is the meaning of this one. Okay, so these are the things. ICMR, OCMR, there is no need to solve this, right? It's already we know about this thing, right? CMR, okay, ratio of those two gains. Now we need to find out the poles and zeros associated with this one. By the way, when we are doing this, it's small signal AC analysis. So how many poles you are seeing? Whenever it's a small signal AC, you can use the half circuit by keeping this one as ground. So one of the part you can remove it. I remove this one. I'm giving V in here. So it becomes circuit like this one. So this circuit looks like this one now. Right? It's a half circuit. This is virtual ground. So how many poles you are seeing now in the circuit? Three poles. Okay. And where are those three locations?
One is at input at D, there is that D.
Okay. as per you it's 1 by 50 times CGS2, right? This is one of the pole, maybe third pole because it's very far. Okay, what about the next one? Where is the next pole? So where it is? Hmm? Okay, V out. So here, if it is here, so what is the value of this capacitor? Hmm? CGD what? CGD of CGD 6. Okay, so it's coming from here, which you for which you have used the Miller. Similarly, this is CGD 8, so that has to go here. CGD 8, then CDS 8 and CDS 6. By the way, CDS is equal to CST. This is what I'm assuming. So these many capacitors will be there. Okay. What about the third one? Here, this. Here we are going to have CGD 2 plus CGD 3 plus CDS 2 plus CDS 3. Any other thing? CGS 6 plus CG, right? Is there anything left? No, right? So in that case, we have three effective capacitors. Three effective capacitors will have three poles. So one pole is already found out. Second one, so 1 by what is the like capacitor resistance RO3 in shunt with RO2 in shunt with infinite resistance if I'm looking here, right? Similarly, at this side, it's 1 by times RO6 in shunt with RO8. Right? Generally, like this output pole has to be far from the second one. Stage by stage, like there is a practice that if you make this like this first stage output capacitor and the pole as 2, sorry, this has to be 1, this is 2, and respective stages will have 3, 4, and all the respective pole at the output of respective stage should be coming first. Like second stage will have the first pole, then third stage, fourth stage, right? It has to be like this. If it is not, then things will not work. Like, as a designer, you will understand. It will come that way only. Otherwise, things will be difficult to design. Okay. So now, if I am asking you, are you following till now, or any problem? Okay. If no problem, then I can ask you. Let's see whether you can answer this or not. If I want to take this one this side and this one this side, is it possible for me to do it with some known theory? How to do it? What do you think? Let's go in a reverse way. So bandwidth is associated with, of course, with pole, right? 3 dB bandwidth is actually the first pole if it is dominated by only one, right? If I want to move this one this side, what should I do? Hmm? Hmm? No, no, look, by hint is here on this slide itself. We can add, look, adding zero. I'm saying that how to design it means without adding any transistor or anything. How can you do that without adding any transistor? Maybe you can tune it, W by L and all these things are allowed. Reduce the capacitance. So how to reduce it? Okay. So as you are saying, this is the tail current. It's a differential structure, let's say. This is the first pole, right? If I'm taking the V out from here, the current flowing through this one is I tail, which I found from here, 1 micro. I'm going to call it I tail. So now what do you want to change? Increase the current. Okay, so that's a better way to start with because that's a fundamental quantity. Changing the current. If I increase this current, like bandwidth, or you can move this pole other side. But to for doing this, you need to increase W by L, right? Because here, if it is like if it is VB, if this is W by L and if this is W by L, if I want to increase by 2, I am going to use M equal to 2 or M equal to 3 or so on, just to increase the bandwidth, right? So this is what we can do. We can increase the current. And similarly, if I want to move the second pole this side, I need to touch the current flowing through this one, right? So in that case, can you comment on the current if this is I1 and if this is I2? If I want omega P1 less than omega P2, what should be the relation of I1 and I2? It should be lesser or it should be higher? Which one has to be lesser? I1 has to be lesser. I1 has to be lesser than I2, right? But if somehow, let's say, if omega P2 is here, and as per our theory of stability, we know that this pole has to be outside to get phase margin greater than 45 degree. What I need to do? I need to increase just I2, right? If I want to tune it or if I want to compensate it and want to keep this pole outside the UG value or on the UG value. So if you are designing a two-stage op-amp, first one has so much of current. If it is not working, you have to increase the second stage current by increasing WL. Just you have to touch the multiplier. No need to touch the WL. The unit value of WL has to be same. Just you are going to change the M, right? From where it's coming. So if it is here 1 micro, sometimes you realize that you need 10 microampere to keep it the required stability. Sometimes you need even lesser than that. But if you're keeping both of them at 1 micro, both the poles are here by the way, right? Then what should be the phase margin in that case? If both the poles are here with minus 40 dB per decade, what will be the phase margin? Somebody gives the correct answer. Yes, Shubham. 0 degree, right? Because two poles at low frequency it's 0 degree, at high frequency it's minus 180 degree because there are two poles. So at UGBW we can assume that it's like this 180. So you have to add 180 more to find out the phase margin. Phase is equal to minus 180 and phase margin equal to 0. Right? So system is unstable. So if you want to make it stabilize, you have to take the second pole outside. For that you need to increase this current. Right? So without touching anything, you need to increase this current. Right? So that's the standard way. Because sometimes some people are doing like they are touching I2 as well as I1 also. So there is no point in like this, one at a time only, not both. So the best practice is fix I1 and then go to I2. Okay, so now all the questions are answered here, right? For this question, illustration 1. If you still could not understand anything, please let me know.
How the current is changing the bandwidth?
Of course.
How is that happening?
Sorry?
How that bandwidth is changing due to changing current?
Yes, but we have to fix it with this required slew rate. You have to fix it with required slew rate. Slew rate is not variable. I'm telling you, like if you want 1 megahertz of bandwidth, and if you are achieving 0.5 megahertz, or I should say that 1 megahertz is already there, but phase margin is equal to 0 degree or something less than 45 degree, then for tuning it, you have to increase the current. So that second pole will be outside UGBW, definitely bandwidth will increase to maybe some other number. But while doing this, till now we have not touched the theory, but the theory says that when you are taking this current, like increasing this current will take this pole this side, but this pole will go inside actually. We will talk about this later when we are going to talk about the pole splitting. I'm just giving you an idea. So bandwidth will be actually not 1 mega, but it will be decreased, and afterwards you need to increase the I1 also. So this will happen for sure. So this one is easy, right? You already know where the pole zeros. If I'm supposed to draw the pole and 0, zero might be at the positive side, right? Right. So these are this is the pole 0 plot where poles are denoted with the cross and zeros with the circle. Right. These all these locations are already known to us. Right? Now the main problem here is, like as I told you, the stability. Stability is actually measured, or it's a function of the ringing. If you know that this kind of output is coming and another output is like this, so which one you will prefer, green one or red one? If you have sufficient time to get settled, so I can choose green one. And green one, which one will have poor phase margin? Poor means less than 45 degree. No, this one has poor phase margin when it's ringing. So phase margin is less than 45 degree, and this must be like phase margin almost 90 degree or something like more than 60 degree. 60 degree will give you around one ring, look like this one. This black color is actually phase margin of 60 degree, and more rings will be increased as you are going lower than 45 degree. At 0 degree, lots of ringing and it's not getting settled down, you will realize that. So we have to have phase margin greater than 45 degree, and for that we need to the second stage current accordingly. Okay, so all these things are happening not in, so we are making Opamp, and Opamp's application are following. One of the popular is negative feedback, right? You keep Opamp in negative feedback and design whatever you want, like filter or amplifier or anything which is whose output is settled. Whereas another one is positive feedback or the Smith trigger, where it's positive feedback and the output is actually hysteresis and yeah, oscillatory, and it's always unstable, right? So this is also one of the application, and if you keep it in open loop, it's a comparator. So here in this study we are only study about negative feedback, right? So if you are keeping your op-amp in negative feedback, what is going to happen? So there might be like many theories. One says that this is V in, this is R1, this is RF. So V out by V in is minus RF by R1 as long as gain is infinity, right? So such structure we want to make from the study which we are doing. So in that case, when it's in closed loop, when we are saying it's in closed loop with like unity gain, what is going to happen? So in open loop gain looks like this one. If you look at, let's assume that Rf by R1 is 1. And if we are drawing two different plots, one plot is about open loop gain, means open loop means only the internal one by removing rest of the things. So if you are drawing that open loop, it will be like this. Or if it is having two-stage op-amp inside, you know that after compensation and all, you will have three poles. One of the pole is available very far, second pole is available at the end of first stage, and third pole is available beyond UGW after doing some compensation or by keeping the second stage current higher than first stage. We can do this, and this is called open loop characteristic, right? Magnitude with respect to frequency. So if we are doing this, how the magnitude response will look like? How much? Do you know the closed loop gain, by the way? It's minus Rf by R1, and that's 1. So if this is 0 dB line, it has to be like this, whose bandwidth is exactly equal to the total bandwidth, and it will follow rest of the poles. But till UGW, closed loop gain is 1 or 0 dB. But this thing is actually depending on following thing: how many poles and zeros are there. So if there is only one pole, the output look like this one. By the way, these slides has been taken from book called Willy Sanson. Okay. So you found that book or no? Okay. I'll give you my book if you want to have Xerox or whatever. So if you look at the open loop is going to give this phase characteristic from 0 to minus 90 around the location of pole, whereas closed loop is going to give this characteristic 0 to minus 90 degree around the UGW if it is only one pole. And you can talk about phase margin. Phase margin is actually plus 90 degree for closed loop, right? Same as like, sorry, phase margin is 135, right? Because this is minus 45. So that is how like you can find out the things, or that is how your closed loop behavior will look like, right? So till UGW you can give the input if this is 1 megahertz till 1 megahertz. If you are applying the input, V out by V in closed loop is equal to 1. After 1 megahertz, it's keep on decreasing, right? With minus 20 dB per decade, right? But what if it is having a two pole system? Means what we studied right now, where only one pole was inside. If there are two poles are inside, like this, if it is two pole, what is going to happen in your opinion? Although answer is given, but it's not straight away answer. You have to find out V out by V in first of all. You have to write down the equation, and then you have to find out this, where V out by V in is A by 1 plus A beta, where A is beta is 1, right? You have to write down the entire A in terms of two poles. And then you can find out what is happening at this. Maybe that one we can talk maybe tomorrow. We'll have it tomorrow. But you can think about it, why there is a big overshoot.
Looking at this output, so what we can infer, like the leakage from the first stage of the second.
One more time, what you say?
What do you think triggers the response?
Okay, this one.
Can we like infer that the leakage is from the second stage?
Leakage. What do you mean by leakage?
Because our gain is gradually increasing. That way it is reaching to the output.
You are saying the closed loop gain or open loop gain?
This configuration.
Yeah, in this configuration, V out by V in has to be 1, right? But what if this is second order system and second pole is inside? That is what I'm asking. So what's your question now?
So question is in the two-stage system.
Mhm.
So near F2, output is increasing. Near F2,
Okay, not near F2. At UGW, it's shooting up.
shooting.
Yeah,
Starting before F2.
yeah.
So somewhere like leakage should be there.
Leakage. What do you mean by leakage? Its
Leakage-
gain is increasing. You see? Maybe I can give you a hint, like what exactly you want. So if it is a, if there is a circuit where it's a second order, if I want to draw the magnitude response with respect to frequency. By the way, do you remember, have we ever discussed that if there is a passive circuit, can you get gain more than 1? Is it possible? But it's possible. It's possible. We can prove it in the laboratory also. Shiva, what do you think? Is it possible or not? If I am doing this circuit Is there any possibility that I'm going to get more than one gain?
Particularly in this case or sir in any passive?
Okay, in any passive.
So there are circuits in voltage doubler or something.
Okay, it's not voltage doubler. I'm saying just RLC circuit where there is no usage of diode. If you don't use diode, I'm talking about only RLC circuit. Is it possible? I should suggest.
At
Hmm.
shoot through you are talking about, sir.
Yeah, gain will be higher than 1.
Transient.
So V out versus V in. Here you are saying that it's going higher, right? Similar thing, can it be possible for RLC circuit? Hmm? Yeah, so but you have to tell me how it's going to happen.
Resonance, the voltage applied will be completely across the resistor. So voltage across capacitor and inductor will cancel out. So we don't know the value. Maybe it can be.
But can it go beyond V in? The question is this one, not the resonance. Resonance condition has to be created. In RLC, how it's possible? You need to have the negative resistance, right? You have to make the oscillator. You need actually somewhere transistor to create that condition, right? Oscillations like Colpit or relaxation oscillator you are saying. So then it's possible, but you need one transistor. I'm talking only about RLC circuit.
In this case, if omega is greater than 1 by LC, I think
Look, you look at the if 1 by CS, still we have time. So this is the thing, right? So pole locations are at plus or minus 1 by root LC, right? Actually, K by root LC, right? In that case, this is not going to happen. Two poles means it will look like this one, where locations are 1 by root LC. So two poles are available here with minus 40 dB per decade. This is going to be same. However, if the system is not like this, if the system is like this, if you can find out this, because this is going to happen in inductor and capacitor, because there are some parasitic resistance and the resistance offered by 50 ohm. All these things create a condition so that your transfer function will look like this one. I suggest you should go with the maybe E203 lectures available online, right? My lectures were maybe 6th or 7th lecture must be talk about this one, where the output look like this one, and this overshoot is equal to 1 by 2 zeta, maybe, right? So if zeta is less than 1, it will shoot up, which is maximum peak overshoot. So it is possible, right? So sometimes like when like in first year I used to give this experiment, inductor and capacitor, and like our student used to see V out more than V in, and they used to say that there is some problem in the oscilloscope, but there is no problem in oscilloscope or at other circuit, right? Because the condition has been created near 1 by root LC, so that this goes higher than the, like V out is higher than V in. If you want, like Saurabh can tell that, right? We did it in the laboratory also for students, and we did this experiment for second year VTEX. We did it. You can also try. This is very simple, inductor and capacitor. If you are going and visiting um, the laboratory,